Good evening, welcome to the last session of today. My name is Arvid, and today I want to talk about multithreading and how to build concurrency primitives from scratch. We've got 60 minutes and lots of content. So, start simple. Why do we need locks and why is this important? Well, in multithreading, we want to guard the shared resources we have from being accessed from multiple threads at the same time. We want to avoid data corruption and data races that way. There's currently a couple ways to avoid this. The most prevalent ways are atomics and locks. And today we want to focus on locks, but we're going to use atomics throughout the talk since they are an important building block of locks, of mutual exclusion locks. Let's quickly start by defining a scenario for locking and exclusive access, where we actually need it. So here's a little example. First, we're defining a shared resource. It's called counter. It's a double. Pretty simple. Then we are creating two threads. We have thread 1 and thread 2. They're both starting and going to increment the counter by 1. This is a read, modify, write operation. Keep that in mind. It's going to read the variable, it's going to increment it by 1, and it's going to write it back again. And then we're joining these two threads, and we're printing out the result. Pretty simple, right? So what do you reckon will the result be? 2, 1, 42, 0? We don't know. Behavior is undefined. We're accessing a shared resource, and we're not guarding it or we're not accessing it atomically. So this means can pretty much print anything. So we need to modify this example a little bit to actually properly guard the shared resource and make this example well-defined. And we're using a variable for that. The variable here is of a pretty nameless type. It's called lock. And we're calling the lock and the unlock function just before we are accessing the resource and just after we're done with accessing the resource. The code between lock and unlock can only be entered by one thread at a time. It is therefore mutually exclusive. Sometimes this section of code is also called a critical section. It's where the lock from Microsoft Windows actually gets its name from. If we now execute this example, or rather we compile it and then we execute it, we will always get the result we are expecting. It will print 2. So with this example equipped, let's have a look at the very first and the most simple implementation of a lock, a spin lock. If you've been to Bryce's talk yesterday, he has implemented a very simple spin lock with just using an std atomic flag. And we're going to do something very similar here, since it is done in pretty much one single slide. It can be written on a single slide. It's really simple, and it will already provide us with this, this guarding, this locking, and make the example well-defined. A spin lock will, as already in the name, spin when there's contention, and we will get to that later down again. So here's the simple prototype or the simple interface for our lock. We have 3 functions here. We have lock, we have try lock, and we have unlock. The lock function will, lock the lock and won't return until we have successfully acquired the lock. Try lock will do the same, except that it returns immediately and will return as a status whether we could acquire the lock or not. And then there's unlock, which will unlock a previously had lock. Keep in mind that you cannot call, or you shouldn't call, unlock before actually acquiring the lock before. This will produce pretty nasty behavior and is actually also undefined. And this pattern is so common that there's actually a concept in the standard library, or rather 2 concepts, lockable and basic lockable. The lockable will provide us with lock, try lock, and unlock, and basic lockable will only contain lock and unlock without the try lock. We will adhere to this concept throughout the whole talk because it means we can use our locks in the utilities of the standard library, like std lockguard or std unique lock. So let's start with building our spin lock. We're starting by adding an atomic. This is an atomic bool. We're not using an atomic flag because we're assuming that std atomic for bool is always going to be lock-free. That is not well defined by the standard. It may be using locks, but in our case, we're going to assume it's lock-free. The true status is indicating that the lock has been held, and false is indicating that the lock has not been held. So it's currently unlocked. And we're initializing it to false. So hence, it is unlocked by default. In the lock function, we are using an atomic exchange to exchange our atomic value from previously false to true. The function will return if it could successfully change the value. That means this while loop will spin as long as the value couldn't be changed by this call, or hasn't been changed by this call. While we're in this loop, we're calling a big macro, shouting macro, thread_pause. This will just pause or tell the processor we're in a busy loop waiting, and it can do some magic to save some energy here and there. This is still not really good, and we will see how we can improve upon this in a couple slides. We're using acquire and release semantics here, as indicated by the std memory order acquire. I will not go into explaining what the atomic memory orders do. Just beware that this basically means that there's no way to actually reorder any read-write before this. We'll continue with implementing the try-lock function. Try-lock is very similar to lock. We will try to change the lock, or we try to change the variable, the atomic variable, to true. If this is successful, then we return the status. We need to negate this because it will indicate with true that the lock has been acquired, and with false that the lock has not been acquired. And then there's unlock, which is rather simple. We're just storing a false value into our atomic, and we're using the release semantics here to ensure the correct ordering with all our other atomic operations. And with this, we've built a simple spin lock, our first lock, and we can see it on a single slide. This is pretty cool, right? So let's quickly talk about the pros and cons of a spin lock, because we now have a lock. Why would you need anything else ever? We can just use this and be done with it. Well, yes, you could do that. And while it's easy to understand and really easy to build, and it's very fast in the uncontended case, which means if you lock the lock, you're just doing a single atomic operation, which can be done in two or three instructions on most CPUs. It is going to be very slow once there's contention. It is spinning in this loop, and it's doing busy work. It's doing nothing, but it's still wasting cycles, and it's using 100% of your CPU. So this is very inefficient. Your kernel, your scheduler, to be exact, will, or may, rather, do some work to unschedule your thread if you spin too long, and you may not be scheduled again for quite a while. So spin locks are best used in kernel space or as a building block of building better locks. So my advice actually is never to use a spin lock directly unless you know what you're doing. So now we're coming back to the spinning part. Spinning on contention. This is the inefficient part of this lock. The unlocking is really efficient because we're only doing a store again. The try lock is really efficient because we're just trying to exchange some atomic variables. But the spinning part, when we are waiting to acquire the lock, is inefficient. It's wasting cycles, and it's possibly resulting in the previously described odd scheduler responses. So let's modify our spin lock, and we call it better lock. And we're calling two new functions here, which have been marked. When the lock is trying to be acquired in the lock function, we're calling sleep thread. Sleep thread will do as the name is, well, saying. It will put the thread currently waiting to sleep. The same thing has to happen in unlock, which means any thread which has been waiting will be awoken by the unlock function to actually acquire the lock again. This is just the idea. This is not actually a working lock. It's just illustrating the idea. You cannot implement it that way. It's sadly a little more complicated. But it is basically demonstrating the idea here and what we're going to implement. This will lead us to a very complicated and very unknown primitive, which is the futex. The futex is originally intended to be from the name of fast user space mutex. So intended as a building block for building mutexes in an efficient and fast way. It works a bit like a semaphore with a maximum count of 1. So imagine that, well, actually, no, there's a little better explanation. The futex is basically a large queue. It's a large lock-free or locked queue, doesn't matter, in which you can put your thread to go to sleep. So in the sleep thread function, we would use the futex to put our thread to sleep. And then in the wake thread function, we would use the futex again to wake this specific thread, which we have been put to sleep, up again. We can actually wake up many threads if we want to, but in our specific case, we only want one thread to wake up and to acquire the lock again. And this is going to be a very important building block for all the threading primitives we're going to build. So let's start by building the futex. We're building the futex by inheriting from a std atomic of uint32. Why this is important will be explained in a couple minutes, a little bit later. For now, just keep track of it. The futex has 3 functions: wait, wait until, and wake. The wait and wait until functions do the work we need to do in sleep thread, and the wake function is for the work in wake thread. So let's have a look at wait. Wait will put the current thread, where this is being called, to sleep if the expected value matches the value in the atomic, which we've been inheriting from. The wait mask, currently set as a default bound to -1, will be saved and will be compared to the wake mask later in the wake call to check if you want to wake up this thread or if you want to keep it sleeping. The wait function returns an enum. 4 values are declared in this enum. We have value changed. Value changed will be returned when the expected value doesn't match the value in the atomic. Awoken will be returned when we have been awoken by a wake event. This is the success state, the return value we actually want usually. Then there's interrupted, which will be returned when we've been interrupted by some sort of signal. And timed out, which is kind of not applicable to wait, but it's going to be applicable to wait until. That's pretty self-explanatory. It will be returned when the deadline has been reached. Then there's wait until, which is kind of like wait. It just includes the deadline and will return timed out if deadline milliseconds have been elapsed. And then there's wake, the third and final function in our futex. Wake will wake up count number of threads. It defaults to int max, which means that we're going to wake up all threads, because we will never have 2 billion threads waiting. And if you have 2 billion threads waiting, I'm actually surprised that how you get that done, and kind of sad that you have 2 billion threads waiting. Wake mask and wait mask. Those are the 2 masks I've been talking about. They are now coming into play. The wake mask here will be compared or will be bit ended with wait mask. And if the bit end between wait mask and wake mask is true, we will wake up the thread. It's going to default to -1, which means all the bits are set. So by default, it will wake up any thread it can find. And in the end, it will return an integer, which is just the number of threads which have been woken up. So let's implement this futex, and let's start by implementing the futex on Linux. And ironically, there's a very aptly named syscall on Linux, which is called, well, futex. It is the actual inspiration of this futex interface, which we've discussed. And therefore, it's pretty simple to implement on Linux, and it is really, really performant. So we can do some pretty good work with it. So let's have a look at the futex syscall. This is the syscall. This is not a function because there's no glibc wrapper for the syscall, which means we will have to call the syscall ourselves. But if we look at this syscall definition, or description rather, we can see it's written as a C function, and we can actually take it as it is and make a wrapper out of that. We just call syscall in the wrapper with the correct syscall number, give it all the arguments, and we're good. Let's quickly go over the arguments because there are a few. And the syscall is not that simple. The syscall itself actually is multiplexing over multiple functions. If you remember, our futex had 3 functions: wait, wait until, and wake. But this is just a single syscall. So for that, we're using the futex underscore op variable here, the int, to give it a bit mask which will define the futex operation. For example, futex wake or futex wait. Then there's uaddress, which is the magic part of that. The uaddress is basically a hash into a big hash table, and this will allow us to create a synchronization primitive out of, well, memory. 1 byte of memory is enough, which we will use to synchronize on. This is pretty amazing because we can just have 1 byte and use it to synchronize and build our locks. Then there's val, which is just the first argument to the futex operation. Timeout, the struct timeout, which will be used, for example, for wait until. Then uaddress true, which is generally null. It is just the address of a second wait queue. And then there's val3, which is the second argument to the operation. So let's start by implementing futex wait. Futex wait is rather simple. We're just going to implement it in terms of wait until. We will set the deadline to -1, indicating that we want to wait forever. And then we're coming to wait until. This is where it's starting to get a little more complicated. We're handing off to the futex syscall. But first, we need to do something. We need to convert the deadline, which is in relative milliseconds from now, into an absolute timestamp, or timespec. We do that by just converting the milliseconds of deadline into a timespec, into called offset here. Then we're going to get the current monotonic clock, and we're going to add it together. The clock underscore add function is a custom function. It's not actually a part of the Linux kernel, or the glibc rather, but it's reasonably simple. This is required because the operation we're doing, the futex wait underscore bitset, which you'll see here, requires an absolute time rather than a relative time. And this is also where we're starting to call into our futex wrapper. We're using this as the key for the futex. So we're using this to identify our wait queue. Then we're setting the OP variable to the correct operation. And we're using also futex underscore private underscore flag, which indicates that this futex is only used in our own process. If you want to omit that, then we can actually use the futex interprocess. And then we're just taking the expected from the function arguments, setting the timeout, which is either null if there's a timeout, or the actual timeout. Then we set uaddress to null, and the third value is the wait mask. Then we're just converting all the return values we're getting back to our previously defined enum. And we're also asserting based on a couple cases which actually shouldn't happen. And this is pretty straightforward. Next we have wake. This is our last function in the futex. And it's following the same pattern as we've seen previously. It's just calling the futex with the correct operations. It is setting the correct arguments, and it's translating the errors. The errors are actually ignored here, which is due to some certain old kernel bugs which have never been fixed. And it will return RC, which contains the number of woken up threads. Self-explanatory. All right, let's do the same on Windows. Sadly, there's no futex on Windows, but there's a pretty good equivalent to futex, and it's called wait on address. If you look at the function call, you realize it's reasonably similar to a futex. It creates a synchronization primitive out of 1, 2, 4, or 8 bytes of memory. It waits for the memory to change until the value is different than compare address, which is just a pointer to bytes of memory again, which, if you think about it, works kind of like the expected from a futex, except that it will also return us the value in the variable later on. Then there's address size, which is just the size of how many bytes of memory we are using, 1, 2, 4, or 8. And then there's milliseconds, which is the timeout we've seen earlier. This time it's actually relative and not absolute. So let's start by implementing the same functions, the same futex functions on Windows. Here you see that this kind of works like futex wait. We're just calling wait on address with the this pointer as the key for our hash table. Then we're setting the undesired value, which is how it's called, to the expected value, telling it that it's size of uint32, 4 bytes, and we're setting the deadline to either infinite, if it's -1, or to the milliseconds. So this is going to return immediately if the value at undesired is different than the value at the current address, and we'll wait otherwise. And then we're just doing the same thing we did with Linux. We will translate the return values into our own result enum, and if our C is true, we will return the success state, which is awoken. Otherwise, we will check whether we have had a changed value, we had a spurious wake up, we had a timeout, or we were interrupted by something else. The wait mask, as you can see here, is currently ignored. You would have to emulate that somehow with a second atomic value, but for the simplicity, I've skipped that here and just ignored it. So then we have the second operation on our futex, which is waking up. On Windows, there's 2 functions to wake up. It is either wake by address single or wake by address all. It will work the same way as a futex. You change the value at the address, and then you call the wake up function. And as the name is already suggesting, we have one function which wakes up a single thread, and one function which wakes up all threads. This is problematic because the futex actually has a way to wake up an arbitrary number of threads. We can emulate that, no problem, but generally you always wake up one thread or all threads. It's actually not much of an issue. We're still going to emulate it by basically checking whether our count is int max, then we will wake up all of them, or if our count is not int max, we will wake up all threads one by one. The return value is not actually 100% correct in the first case, because we're going to return int max, which is different from the threads we've been woken up. It's somewhat correct in the second case, though. But this is not much of a problem. The return value is not used too often. So let's look at the other operating systems. We have a problem, as you see, with the wait mask and the wake mask. As you also see here, the wake mask is ignored. And we have also a problem on macOS, where there's no real good alternative to wait on address, or futexes. So let's actually have a deeper look into how futex work by emulating the futex on all the operating systems. So we have a single implementation which will work on all operating systems and is actually comprised of standard C++. For that, we're going to implement something called a parking lot. So this name may sound funny at first, but if you think about it, it actually makes sense. I also didn't come up with that name. So we have a queue of threads, which we can think of as the parking lot. And then we have threads, which you can think of as the cars. When you park a car or put a thread to sleep, you put it in the parking lot. You drive there, you get out of the car, you do your shopping or whatever, and you come back and you unpark your car and drive away. You put your thread to sleep, then you do some work, something else in parallel, then you come back and unsleep it or wake it up. So this kind of sounds like a futex, right? And it kind of is. It's a little more dynamic. It allows for more certain things because the interface is the interface is a little more not so strict. And we're going to implement the parking lot by going from the bottom to the top. So you can see here again, the parking lot consists of a wait queue, and this wait queue consists of several wait nodes. The wait nodes are the sleeping threads. So let's have a look at the wait nodes. We're starting by creating a base class, wait node base. It has a couple member variables. It has a next pointer, a previous pointer, it has a key, and it has a lot ID. So it has the next and the previous pointer because it's going to be part of our wait queue. Our wait queue is a doubly linked list. So this means, rather it is an intrusive doubly linked list, which means that the wait node needs to have next and previous pointers for the next node and the previous node. The key is the index used in the bucket, or rather the queue, and it's also used to later get access to the queue. It is saved so we can identify to which queue this wait node is actually attached. And the lot ID is used for the same thing. It is just a single ID for each parking lot. If you create a new parking lot, we're getting a new ID, and this ID is used to identify it. And the constructor is just initializing both. So now we're getting to the missing piece of the puzzle, and that is the waking up and sleeping of our threads. This is the part which the futex did before. We're now using a std mutex and a std conditional variable to emulate the two operations we had on our futex, the wait operation and the wake operation. We're going to implement wait for and wake here. We're not implementing wait because we can, again, use the wait for interface for the same purpose by just setting wait ms to -1, indicating that we want to sleep forever. So let's have a look what a conditional variable is and how we can actually use it to emulate a futex in standard C++. So this is a CPP reference. What we have here is the condition variable class is a synchronization primitive that can be used to block a thread or multiple threads at the same time until another thread both modifies the shared variable, the condition, and notifies the condition variable. This sounds a lot like a futex, right? And it indeed is very, very similar. The shared variable in our case is what we had here is the m_signaled, the boolean. We will set that to true if we've been signaled or if we've been woken up. So let's have a look how this actually looks like in practice. This is the wait for function of our wait node base. We are creating a unique lock for our mutex and locking our mutex. Then we are creating a loop. This is the while loop where we are staying in. We are looping as long as the signal is false. We have not been signaled. This is the shared variable. And as long as the status is not timeout. This is guarding against spurious wake-ups. Spurious wake-ups occur in conditional variables because the scheduler may not be 100% certain that you've been woken up and will wake you up anyway. We need to check whether we have been woken up by accident or we've been woken up by a threat which actually wants to wake us up. And this is why this loop is here. In this loop, we're simply checking whether wait ms is -1 or not -1 to call the correct functions on our condition variable. If wait ms is not -1, we are waiting on the condition variable for as many milliseconds as the variable is indicating. If not, we are waiting forever. The wait operations will atomically release the mutex which we have acquired earlier, and suspend the thread. So they block and may not return for quite a while. So if the thread is awakened after we've acquired the mutex, we will return the status, as you can see here. This will happen under the circumstance that we've been called from wake. We've been awoken from wake. And this is pretty much half the magic we need. Now we need the other half, which is wake. So the wake up is pretty simple, actually. We're acquiring the same mutex. Remember, the mutex is guarding our shared resource, our boolean. We can only modify this boolean because it is not atomic under the mutex. We're using a lock guard here. There's no need for a unique lock. And we're setting it to true. And then we're calling notify1. Notify1 will then wake up a single thread, and the previously shown function here will return. So this is the first part of our parking lot. This is the wait node. Now let's have a look at the wait queue. Remember how the futex syscall, the first argument of the futex syscall and the first argument of the wait on address syscall, they had a key, or rather an address. And this key was a key into a hash table. And this hash table was returning us what we're now going to build, a wait queue. So each element in this hash table is a wait queue. For that, we're going to create a struct wait queue. It is, as previously said, a doubly linked list. It's not even a doubly linked list, which is lock-free. It has a lock, it has a mutex, but that doesn't matter because we don't really need it to be super fast, since it's only going to be accessed when we want to put something to sleep. So it's the slow path anyway. There's an atomic integer called m_count, which is keeping count of how many elements there are in this wait queue. And we have two functions, pushback and erase. They are pretty self-explanatory probably. We have pushback, which will add a new element, and we have erase, which will remove an element from our wait queue. And now we need a way to access our wait queues. For that, we're just creating a static function, or the global function, called getQ. GetQ will take the key, which is the first argument to the futex syscall, remember, and we'll use it as an index into a large array. Here I'm being lazy and just statically allocating a large array of 4096 queues. It must be power of 2 because we're using bit-end operations here to index into it. And 4096 is just some number I made up because it's a nice number. You can experiment with that. You shouldn't have too few, but you shouldn't have too many either because it's taking quite a bit of memory every startup. But you want to avoid to have too few, so you want to avoid having clashes. You don't want to return the same wait queue for every single parking lot. And now finally, let's have a look at the parking lot. So, the parking lot class has a single variable, and that is the lot ID. This is the ID we've been talking about earlier, which is in the wait node base. And it's just allocated from atomic variable, which is called ID allocator, or rather ID cache, sorry. And it's just a number which is going to increase the more parking lots we have. Just some sort of ID. It is templated on data. Data is currently defaulting to detail empty. Detail empty is a single struct, which has no data in there, and just some comparison operators so we can use it. But we will make use of the data variable, the data template argument later. So let's actually build the wait node, which we've been waiting for. So we're inheriting from our wait node base, which we've been building before, and we're adding a single variable here. And this is the data we have been templated on. We will use that for the wait mask, which we've been seeing in the futex syscall. So we can perfectly emulate the syscall. The constructor is just constructing it with a key, a lot ID, and the data. Next, we have the first interesting function, and that is park4. This is the equivalent to futex wait, or rather futex wait bit set. And it is templated quite a bit, and it has a few arguments. So let's quickly go over them. The key here, again, is the key or the bits, the argument to index into the hash table which is used from the previously built getQ function. Then we have data, which is the data which is going to be inserted into the wait node. In our later example, this is going to be wait mask. Then there's park condition. Park condition is a lambda. Park condition will be called before we are parking our threads. This is similar to the expected of our futex. And it is basically for the reason here that we want to prevent lost wake-ups. So this means if we are currently in the process of putting a thread to sleep, but another thread has modified this atomic variable of our futex in the meanwhile, and we don't actually need to be put to sleep anymore, this will prevent it, because this will be called right at the second before it happens. Then there's pre-wait, which is another lambda, which is going to be called right before we're putting to actual sleep. It's not going to prevent anything, it's going to return void. It's just for utility later on. And we will use it in our implementation of a conditional variable. And then there again is the timeout, which is a relative timeout in milliseconds. So let's start by implementing the park_for function. We start by grabbing the key. We're doing that by hashing the bits, which is just the variable key renamed. And we grab the associated Q from our getQ function. With that, we are creating our wait node. This is the wait node we're going to add, or we're going to link into our doubly linked list. Then we are incrementing the count of elements in our queue, and we're going to acquire the lock of the queue. Since remember, the queue is not lock-free, we need to have the lock acquired to modify it. Then we are calling the previously mentioned lambda, the park condition lambda. If the lambda returns false, we're aborting and basically don't push it into our queue. We do that by unlocking the lock again. We're decrementing the count, and we're returning park result skip. If it's been successful, we push the node to the queue, and we relinquish the lock. So you can see here we had a little scope introduced there, and if the lock is now getting destructed, we will relinquish it, and it will be unlocked again. Next, we're calling the mentioned prewait function. This is, again, the return value is not used. It is just used for certain implementations. Again, we will see that later. So then we have the actual waiting, the actual sleeping. This is calling the wait_for function, which we've been previously building in our wait node. The timeout MS is passed, and we will wait. This is a blocking call, and we will stay here until we've been woken up. If we've been woken up, we will check the status immediately. If we got a timeout, we're acquiring the lock of our queue again. And we're checking whether we have been signaled or not. If we have not been signaled, then this was an actual timeout. We're going to erase, we're going to remove, we unlink the node from our queue, and return timeout. If we have actually been signaled, then this is not really a timeout. We're just going to skip it, and we're going to return success. So, now that we have park, we need to have the opposite, unpark. Here, key is the same as used for park_for, and unparker is a lambda again. Unparker is a little more complicated, or a little more interesting actually. It's called with the current value of the wait node, the data in the wait node, and returns a control value. So we can control what we want to do. And these are the 4 options we have. We can return, retain, continue, which means this thread is going to be kept parked, and we continue unparking. We want to unpark a different thread. It's not matching our criteria. We can return remove continue, which will remove the thread, but continue unparking. Then there's retain break, keeping the thread parked, and we want to stop unparking. And remove break, which is removing the unparked thread and won't unpark any other. This control will allow us to emulate the wait and wake mask in our futex, which we've seen before. So let's start by implementing the unpark function. Unpark, again, is getting the key and getting the queue. We've seen that before. Then there's an early return. And this early return is checking the count of the queue. If the queue is actually holding no elements, we have been unparked before, or concurrently, since remember, everything is atomic here, and we have multiple threads. So this means there's nothing to unpark anymore, just return. Early exit, simple. If there are elements in the queue, well, we need to acquire the lock of the queue, and we need to iterate through all the elements of this doubly linked list. Simple iteration, we grab the node, set the next pointer, and we will look at the node. And this is why suddenly the saved key and the lot ID were important, because we need to make sure that the node we are currently accessing is actually associated to our parking lot. Since remember, the getQueue function may return the same queue for the same key, or for different keys, sorry. The same queue for different keys, because, well, it's a hash table. So we need to make sure that we got the correct node. We're calling the function, which is the unparker function, with the data in the node. And we're getting the result. And now the results from the control enum are getting of interest. If the result is either remove break or remove continue, we're going to remove the node from our doubly linked list, and we're going to wake it up. But we're not going to destroy it, because the caller is going to destroy it. And we're also continuing the cycle. So we're going to continue looking at nodes, and we're going to continue calling the unparker function, and we can continue unlocking or waking up other nodes. But if our result is remove break or retain break, we're going to break, and we stop the loop, and we don't continue looping through our nodes. We're done here. So with that parking lot, we can now emulate our futexes. This means we have futex, we have the futex interface on Windows, on Linux, on Mac, on Android, on iOS, on BSD, whatever you can think of. But we need to still build the interface for it. But this is rather simple. We have emulated futex wake and emulated futex until. Single function, because in this case I decided to not split it, since if you set wait mask to, if you set, sorry, monotime to null, you can just indicate that there's no waiting. So let's have a look at emulated futex wake. We are calling the unpark function. And here I'm using a global cache of parking lots, which are created at the beginning of the program. And this is the unparker function, which we've been talking about before. Here we are doing the same check which the futex is doing internally. We're checking mask and wait mask, and if they are 0, if the result is 0, then we are continuing unparking, because this is not the node we want to unpark. If this is not 0, then we found a node which we want to unpark, and we're going to unpark it. We're going to decrement the count by 1, and we're going to increment the woken by 1. If the count is greater than 0, we continue. If the count is 0, we stop. And then, last but not least, we return the number of threads which have been woken up. Then there's emulated futex wait. Pretty similar. We branch whether there is a timeout or not, and we call park until if there is a timeout, and we're going to call park if there's no timeout. The function here, the first lambda here, is the park condition which we've been talking about. The park condition is checking whether the futex is matching the expected value. And this is exactly the same behavior as our Linux futex. And then we translate the results of our parking lot into the results of our emulated futex, and we're going to return it. So now we can finally have a look at building our first actual threading primitive, which we've been waiting for all time. So let's have a look where we can actually use the tools we've been building so far to build our own mutex without using the pthread primitives or the standard mutex. And we're going to take a look at the fast part. We are trying to avoid switches into kernel space by taking the spin lock we've been developing first and integrating it into our mutex, which means we will first try to spin a little bit while trying to acquiring the lock. And if we can't do that, we only then will suspend and sleep. This means if the contention is really quick, so you have the lock for maybe setting a single variable, then you may not ever actually switch to kernel space, and hence reducing the time you're spinning or you're waiting. We're using the same interface as before, the lock, try lock, and unlock, and we're again inheriting from std atomic. And we have two helper functions, lock impl and unlock impl, which are the actual implementations. We'll see where we're still inheriting from the atomic interface in a second. But first, let's have a look at the lock function. As mentioned, we will use parts of our spin lock to speed up the uncontended path. So here we are in a CAS loop, a compare exchange, which will load the current state of the atomic. Then it will check whether the lock is currently locked. And if it is not currently locked, it will try to set it to be locked. And if this is successful, we will just return. This means we just acquired the lock without doing any calls to any system, to any kernel, or to our parking lot, or to anything else. This is all we need in the uncontended case, and it's incredibly fast. Yeah, if locked, we will fail here, and we call into the kernel if we are locked. So again, if we locked, we fail here. And we go into the kernel here. This means in the case there's contention, the lock is currently already locked, we will need to look into lock impl to actually implement the locking mechanism with our parking lot or our futex implementation. We will look into lock impl next. But first, let's have a look at try lock. Because try lock is pretty much the same thing without actually having the lock impl. Because try lock will never actually need to go to the contended case. It's only the exchange loop and will return either true if the lock could be acquired, or false if the lock could not be acquired. So let's look at lock impl, which is the actual nitty-gritty detail of this mutex implementation. So this is pretty similar to what Bryce presented yesterday in his spin lock implementation. We have a limit of times, of how many times we want to spin, and of how many times we want to yield. And then there's the spin count. These numbers are equally made up, although they have been tested on several architectures and have been verified that they actually work pretty well and don't interfere too much. But this can always be tweaked for your use case. So if your contention is profiled to be much longer, you can maybe turn the spin limit up a little bit to spin longer, and therefore reduce calls to the kernel. So here's our retry loop. This is a big loop with goto. This is scary, sorry. I'm old school, I use goto. So what we have here is we are looking at the old state, the state we've been loading from our atomic. If it is currently not locked, or rather if it is currently locked, then we are jumping in here, and if the spin count is greater than the spin limit and the yield limit, we will yield or spin. We will suspend. But if it's lower, we will yield or spin. And this is what we're doing here. We're calling thread pause again. This is what we've seen in the spin lock earlier. Thread pause is pretty inefficient. It's just spinning there, calling a single assembly instruction. But if we can actually yield, if the spin count is greater than spin limit, so over 1000, we will yield. So thread pause is faster than yield. Yield is faster than suspending. And therefore, this is the hierarchy of steps we do. So this is kind of like a waterfall. If at first we can spin for a while, we spin. If we can't spin anymore, we yield. If we can't yield anymore, we suspend. And this is all because we want to have the fast path optimized to be as fast as possible. So let's have a look at the actual case where we have spun 1,000 times, we have suspended once, we have yielded once, sorry, and then we need to suspend. We will try to park the thread after we've we've actually checked again whether the lock is still held. So here we are checking whether the KS parked flag has been added. Because if the KS parked flag has already been added, we're going to retry because the thread may have been unlocked in the meanwhile. If we actually successfully change the atomic, we can park the thread. This again is a blocking call. It is setting the futex atomic to KS locked, and we'll park the thread. Once the thread has been awoken, we will drop down again, like we did before, and retry. So here we actually may spin again, yield again, or go back to sleep. The reason for that is that a different thread may have been acquired the lock in the meanwhile. This is not a fair lock. This is an unfair lock, how you may call it. There are cases where you can get stuck in here if you're not fast enough to acquire the lock again, and some other thread is acquiring the lock over and over again. There are cases where you can resolve this, but this is out of the scope. There is a shared mutex which I have built, which is being a fair lock. Once we actually have acquired the lock and have been woken up again, we can indicate that in our atomic variable. This again is the same thing we did in try lock and at the first time in lock. Same CS loop, just setting the new state here, and if it is successful, we just drop out of the function and we're done. We've acquired the lock finally after all this ordeal, and we're done. If we still can't change this, we go back again. So because someone again has acquired the lock before us, we were too slow, we go back again and to start the whole ordeal again. But if everything went well, we've acquired the lock, and we'll drop out of this function, and we finally can actually access our shared resource. So of course, we need the equivalent of unlock. Unlock is not as simple as it seems, but we need to make sure that they're actually waiting threads to be woken up. Because if we will just wake up any threads, we are wasting cycles by waking up threads which have not been sleeping. We're waking threads up which are not there. We will jump into the kernel to wake up threads which are not there, which is inefficient. So we again need to check whether the atomic, the value here, is actually indicating that there are any parked threads. So we're setting it to be unlocked, and if it has not been acquired, if it's not been changed, we will loop and we try it again. If we can actually change the value here in this loop, then we check it, and we check if there's any parked threads before, and if there's any parked threads, we will have to unpark them. Any sleeping threads need to be woken up, otherwise we may get a deadlock. So we need to give them a chance of acquiring the lock, and need to take a look at the unlock implementation. The unlock actually is surprisingly simple. We're just unlocking the first thread we find, and we're done. This is the whole unlock of our mutex lock. This is the same function. We're ignoring the mask, we're ignoring the data. We can just take the first one, remove it, and break. And with that, we are done with building our fast mutex. And I think I still have time, so I can actually build a condition variable. This is great. So let's have a look at implementing a condition variable. So you're telling me we're not going to implement a condition variable using a condition variable? Oh yeah, actually I'm doing. So we're going to implement a condition variable using the futex, the emulated futex, which is using a condition variable. Yeah. Anyway, let's continue. So this is the standard condition variable interface. Wait for, notify one, and notify all. Simple. So let's have a look at wait. Wait is just largely parking the thread. We check whether we own the lock. If not, we are asserting. And I think the standard actually throws here. I don't know. We're asserting that the lock has been acquired. Because remember, the condition variable is guarding some sort of shared resource with a std mutex or some sort of lock. So we're checking whether that's been acquired. We're just parking it, and we are calling again the park condition lambda. In this case, actually, we just return true hard-coded, because we don't care about lost wake-ups here. This is really not a problem. We want to put this thread to sleep. We want to wait no matter what. It's fine. The atomic is set to true, which is basically indicating that there is currently a waiting thread, which may need to be woken up later. And we are now also using the second lambda, which is the pre-wait lambda. And this will just unlock the unique lock, meaning that the owner of this condition variable and this mutex, or this fast mutex maybe, can actually modify the shared resource. And once park returns, which means we've been woken up, we will lock the lambda again and return from the function. This is exactly as the condition variable function is explained on CVP reference. So if you ever looked at that, you can see that this is exactly what we just built. So let's implement wait for. And wait for is essentially like wait. We're just calling park for instead of park. Simple. And we're returning different results. So then there's notify one. Notify one checks whether there's actually any waiting threads. If not, we're returning immediately. Simple. If there's any waiting thread, we will just remove the first one and return from the function. Notify all, just like notify one. We check if there's any threads waiting, and then we return all of them. Since we're returning, remove continue here. And we're also setting the atomic to 0 again, because with notify all, we can be sure that we've removed all the threads. And notify one, the comment is indicating that we're not setting it to 0, meaning that there could still be other threads. Only notify all can do that. And with that, time is over, and I'm done. Thank you very much. Maybe a couple minutes for questions. If somebody asks a question.
Does anyone have a question?
All right, it's late. Let's have dinner. Thank you very much. Enjoy the conference.